Okay, perfect. Um, so let's get started. Thanks everyone for joining us today for our webinar on strategies to mitigate battery defects using JuliaSim or more specifically manufacturing defects. And so this isn't this my name is Ranjan and this is my colleague Marc. So the first thing to say is that this isn't a webinar about defect detection, but really it's a webinar about what do you do once you detect the defects. Is there a way you can propagate these defects into a functional performance model of a cell or a pack and understand the implications on, let's say, cycle life of the cell. So this is one webinar in a series of webinars. So just a couple of weeks ago we did a webinar on simulating large battery packs and gave you a bit of insight into how you can do that with JuliaSim batteries. With this one, we are going to talk about really uncertainty quantification, right? Forward uncertainty quantification that arises from defects. And we'll have another webinar next week, talking about how you can swap in and swap out different chemistries using JuliaSim batteries as well. Right. So defects are a big deal in lithium ion battery manufacturing. So it's a huge topic, and especially when you're at the start of a production plant, when you're sort of building up a new plant from scratch, you tend to get a lot of scrap as you start the manufacturing process, and this scrap could range between 5 to 30% or even higher. And there's a lot of work that needs to happen to maximize the yield of the manufacturing process and to reduce scrap. And what we're going to do today is try and understand what are the defects that occur during the manufacturing process. So, well, for example, within in the manufacturing process, you're usually manufacturing your electrodes, and you're assembling the cell together. And during the process of manufacturing the electrodes, you could have a number of different defects, point defects, line defects, and all of these can affect the cell performance in many ways. So in particular, the two big ones that you might have heard in the news as well is in addition to affecting the lifetime of your cell, or reduced performance of your cell, is a risk of thermal runaway and fires. So there's been plenty of news articles of fires at different manufacturing plants, and sometimes improperly validated battery packs have been sent out to customers, and then re-rolls have had to happen as well. So these are really important sort of safety concerns that we should think about, in addition to actually thinking about the reduced lifetime of performance of the battery cell. So in that sense, we're going to think about defects in two different axes. One is whether a defect is critical or non-critical. So is a defect critical enough such that a cell with that defect will have to go to scrap, or is the defect non-critical such that you get some sort of inhomogeneity in the aging characteristics and the performance of the cell. So these are sort of the two axes that we're going to think about these defects. And really, what we want to do now is try and reduce the amount of scrap that comes from the manufacturing process. So, for example, if you have a plant and that produces several batches of cells, is there a way we can look at this batch of cells and qualify it and understand whether this batch is meeting the spec of a certain customer or not, right? And if it is, well, that's perfect, and we can use our we can use modeling as a tool to understand whether it is actually meeting the spec. And for example, if you have a product with with non-critical defects, we can understand how much it affects the cell performance, and then perhaps even reuse this a batch with non-critical defects, and sort of commercialize it as second grade goods. So even if you can't meet the spec of a certain customer, perhaps there is another customer who would find such a batch useful, and so you can commercialize it at a discount, so to speak. So that's sort of what we're trying to enable with our performance models, to try and make sure that we can reduce scrap and to understand the inhomogeneities within a batch of batteries. So what are the ranges of lifetimes that you might expect from a batch of batteries, given the defects that you observe in the batch? And with this knowledge, one can understand whether which defects are critical and which defects are not. And we'll comment a little bit on how we figure this out with modeling and analysis in the future. So when we talk about defects, there's yet another way to think about them, we like to think about them in these two axes of bias and variance. So how are you so like does the batch, for example, have a different like let's say you're concerned about, let's say, the cathode thickness, right? And does the batch of cells have a different mean from the cathode thickness that was provided to you as a spec, right? And this sort of indicates a drift in the manufacturing process. The other sort of problem is variance, right? Like how do you why is there high variance in the manufacturing process? And if there is high variance, what are the downstream effects? And so if you look at the picture on the left here, you can look at the top left icon there is the gold standard with low bias and low variance. But then as soon as you start to increase the variance, the picture on the top right, you see a certain spread. And then, of course, if you have a high bias, you have a drift in the manufacturing process. And then the high variance and high bias is the worst of two worlds, worst of both worlds, so to speak. So now that we sort of have established a baseline on what are the things we're thinking about, like in terms of what are the kinds of defects we're thinking about, and usually at this stage we're usually thinking about the proportion of active material in the cell, or let's say let's say some variation in the thicknesses of the electrodes or separators. So now that, let's say we have a batch of batteries, right? And let's say we have data on all of these different metrics. What do we do with this data? And with that context, I'd like to introduce to you the JuliaSim Batteries app. As I introduce this app to you, I should tell you first about JuliaHub. So we're a company that makes modeling tools, and all of our modeling tools are hosted on a platform called JuliaHub. Right now, I'm running the internal version of JuliaHub here, but you could go to JuliaHub.com, and if you hit explore packages, you'll be able to get a compute environment that you can interact with for free today. But right now I'm showing you our internal version as we show you these demos, on the platform here. So the first thing to understand of the platform is a place where you store apps, and or you can launch apps from. It's in that sense it becomes a compute engine as well. Today the app that we're going to think about, or we're going to understand, is the JuliaSim Batteries app. And of course, you can do a whole bunch of other things on the platform as well, such as creating notebooks, sharing these notebooks with folks, creating projects that serve as these sort of shared development environments with your coworkers, and of course jobs, right? And these are sort of the sort of the workhorse of JuliaHub as a compute engine. So you can spawn lots of computational jobs on JuliaHub and then collect the results within your main working node. So it's sort of HPC on demand in some sense. Anyway, so we've hosted the Batteries app on this platform. And the first thing I want to do is to quickly show you what that is. So this is JuliaSim Batteries, the app. And there's a few things you can do here. So there are three main tabs as such, right? So the first is to specify a cell or a specific configuration of a cell. And if you increase this number here, then you're now talking about a pack instead. So the first thing you can do is choose a model, and we're choosing the sort of very popular standard DFN model, Deuel-Fuller-Newman model. And once you do that, you can choose a chemistry preset. We have three chemistry presets as of now: LCO, LFP, and NMC. And so for this demo, we are choosing NMC. The software comes with an SEI capacity fade degradation model built in, as well as a simple thermal model. And then once you specify the cell configuration, you can then move to the experiments tab, where you are now specifying a certain charging and discharging protocol. So for example, if you wanted to understand the lifetime of this cell that you have now designed, you can charge it and discharge it multiple times, and then sort of look at the expected lifetime there. So in this particular case, we're discharging at a rate of 0.5 C and sort of charging it at a rate of 2 C, and we're cycling the cell multiple times. And well, as soon as you specify this, you can then head to the analysis tab and then sort of see you sort of very quickly get some results on the expected lifetime or the cycle life of the cell. So you can see that within 350 cycles, the state of this is the state of health of this battery cell has gone down to less than 0.8. So we've sort of already reached end of life. So you can do analysis like these within the JuliaSim Batteries app. Now, when you're starting to think about defects, the way to think about them is perhaps a distribution of parameters. So if let's say I'm a battery manufacturing plant and I'm producing batches of cells, every day, I collect a bunch of data on these cells. So let's say I have an Excel sheet that gets produced with each batch, and I have a number of different measurements of the cathode, of the anode thickness, cathode thickness, the separator thickness, and the active material fractions. And so let's say we've produced a batch of 100 cells, and we have numbers on all of this, right? And with this simple sort of Excel plot, you're able to see what this roughly looks like and how much variance there is, and we've computed some standard deviations and metrics here. So let's say I want to characterize this batch with the JuliaSim Batteries app. And of course we have multiple batches, you can see. So what I can do is go to my app, go to the configuration, and hit advanced options. And so you see that when you click on the advanced options button, you have a simple sort of representation of our battery here. And so you can you can click on any of the components here, and then that'll pull up a drop down of parameters, right? And so what we would do is choose from this drop down here. Let's say I'm thinking about the active material fraction. and I can now specify it as a distribution. And so now, once I choose from this drop down and find and specify in the normal distribution, I can then, let's say, enter a certain variance or a certain standard deviation that that I've observed from my batch of cells, right? And I can go down, I can change a bunch of different things here, but for the purposes of this discussion, we're mostly thinking about the we're mostly thinking about the thickness, the cathode thickness, as well as the active material fraction. So let's say your cathode active material fraction varies by 1 micron, right? So this is how you specify the distributions within the within the battery app. In a future iteration, we'll probably have a way for you to just directly upload the Excel sheet there, and then read off the different standard metrics. That's fairly straightforward. But for this demonstration, we're sort of entering this directly. But so then once you do that, you can just run the same experiment and then run the analysis. And then what this is going to do is take this input distribution, run it a few times, run it a few hundreds of times, in fact, and then give you some data which you can then hit download on this, and you'll get an Excel sheet back. So I've hit download on this, and I've gotten, let's say, I've gotten some data from the app. This data is effectively a histogram of various quantities. So that's what you would hope to expect. So I could unzip this and just sort of look at these various metrics that I've gotten as a CSV here. So this is roughly the workflow that you could expect from the JuliaSim Batteries app. So in terms of so my colleague Marc will take a look at a specific batch of batteries and some results from it, and we can discuss those results in detail. But before I hand it off to him, just wanted to see if there are any questions so far. I think there is one question. So what are the advanced options? So yeah, the advanced options was, we have a question of what the advanced options are, but the advanced options have all of the various, all of these various parameters, some of which are these geometric parameters, which we used, which we just varied live in front of you. So, so that's what that's what these are. Yeah, are there any further questions? Otherwise, I shall hand it off to Marc, and he will discuss some of these results, and you can slowly understand how you could take this data and then understand which defects are in your batch and whether they're critical or non-critical. All right, let's see if there are any questions. I don't see any. So yeah, so I'll just hand it off to Marc, and yeah, Marc, take it away.
So thanks, Ranjan, for presenting the introduction and the JuliaSim Batteries GUI.
Wait a sec. Marc, I'm not sure I can hear you. Maybe it's on my end. Oh, okay. Never mind. That's just on my end.
I can hear Marc. Yeah, he's audible.
Perfect. Go for it. Yeah.
Okay, great. So one of the things that we can do with this JuliaSim Batteries GUI is take a look at different kinds of defects. So we mentioned this trade-off between bias and variance that you can get in manufacturing and in other cases. So with the GUI, we can very simply and very easily test what happens for these different batches where we may have different specs, different quality assurance that we get as a result of our manufacturing process. So for this first batch, we had low variance in our parameters, but there were high bias. So we were a little bit off spec with our process. So in this system, what we see is that even though we're a little bit off spec, because we have such low variance, if we look at the distribution of all of our cells from this batch, they have a pretty good state of health. And the reason for this is that all the cells are behaving roughly similarly. However, if we take a look at the other case, where we have a very high variance and a low bias, we see a very different trend here. So what we see in this case is because our variance is very large, this propagates throughout the simulation. And once we reach 350 cycles, we have a very large deviation in our state of health. So on the next slide, we show how you can treat this as an actionable metric in your manufacturing process. So previously, we were showing how you can just take the defects which you simply have for your batch and try to understand what the state of health would be for that batch with some charge and discharge protocol. But now we want to kind of flip the question on its head and answer the question that we posed originally of which defects are truly important for my situation. And what defects do I need to really target in on in order to get a batch of cells which fits my needs, and I can safely ship to customers and get good performance down the line. So we're going to repeat the same analysis that we showed previously. However, we're only going to look at a certain subset of the parameters. So the first one we're going to look at is only these defects on the anode, and then we're going to look at only the defects on the cathode. So here we can see that this full set of defects on the left-hand side, we get a very similar distribution and trend as those only on the anode. And if we look at the cathodes plot on the right-hand side, we see that there's a very small deviation, even though the overall variation in these parameters is considered pretty high. So what we can determine from this kind of analysis, just based on changing some of these key defect parameters from our different batches and via simulation, is that the anode is really the main dominant source of the variation in state of health. And if we're going to make any process, we want to look at just affecting the anode and seeing if we can get better specs just on the anode. So if you click through a little bit more and bring us to the next slide. So in conclusion, this JuliaSim Batteries app gives you a really powerful tool on making manufacturing analyses that look at defects and different charging and discharging scenarios very easy. So you can look at all kinds of defects, whether those are off spec or just those leading to high variance, which may influence your decision on which customers to submit it to. And it gives you a tool to really narrow in and identify the defects that truly matter for your system, that give you an actionable tool in designing and manufacturing your batteries. So with JuliaSim Batteries, we really want to make it work for you and your use case. So one of the things that we're offering is a short-term engagement with the JuliaSim Batteries team that takes your cell models and your data and can scale it all the way to the pack. You can run these same kind of custom analyses with various charge and discharge protocols using the model that we validate for your purposes. In addition, we can offer support and training methods to generate custom reports, as well as a dedicated SOC 2 compliant test bench that we run on the JuliaHub cloud computing platform. So with that, thanks for your attention, and we're happy to answer any questions.
Yeah, thanks for that, Mark. So do you would you say that you could let's say you could look at any of the parameters that we looked at the GUI, right? Like in the GUI, we had like a ton of parameters there. Like, can we understand the sort of sensitivity or or defects in any of the parameters that are listed there? Like, there's there again like 20-30 of them, right? Like, is that the workflow you would is that the kind of possibility that you're suggesting with
Yeah,
the
so in this example, we just showed variation on the thicknesses and the electrode and separator, as well as in the active material. But there's no limit to the kinds of defects or even the distribution for your defects. So if you had a bimodal distribution and you wanted to input values for that, you're free to select that for yeah, any kind of simulation.
So I have a question on like when you simulate a cycle, how many time steps are chosen for a particular cycle? Could you answer that?
Yeah, so in JuliaSim and JuliaSim batteries, we use these advanced ODE or ordinary differential equation and differential algebraic equation solvers, which are adaptive time steps. So we don't pick the time step ourselves, the modelers. These are just determined via simulation, and we're solving very stiff problems here. So it can adaptively change the time step to deal with that stiffness.
Yeah, so the second part of that question is whether we could show the GUI once more. So let me maybe switch to that again. So so just typically and again, like if we're happy to sort of get on schedule something offline with you if you'd like to go through a detailed step-by-step simulation of the GUI. But just to recap, it's mostly a setup, a problem setup, tab, an experiments tab, and the analysis tab, which just runs the forward simulation. So we're, and that internally will call our batteries backend and then simulate a set of DAEs as Marc just describes with adaptive time stepping. But I mean, yeah, we're happy to get on like to connect offline and to show you the full app and what it's capable of. But largely speaking, you can get full lifetime simulations of with the DFN model in about a few seconds, and yeah, and you could get pack level simulations with an SPM model, or charge, charge cycles of a 1,000-cell pack in a few seconds as well. So we're happy to show, set up a specific demo for you. So there's another, okay, so to what extent are these predictions backed by actual life testing data?
Yeah, so in this example we showed, we picked a few common defects. So one of the examples is like the thicknesses. Those are commonly in variation on the order of 1 or 2 or 3 microns or so, as well as the coding for these things. So I think there's an important question in there, though, of how do you make sure that your degradation curves and all these types of information are also backed by data. So one of the things that we offer in JuliaSim batteries is this combination of the physics-based model, which is based on these DFN or SPM models, as well as including some machine learning pieces in places where we know that the models don't do quite so well. So, for example, one of the places where these models typically fail is in low temperature performance or in long-term degradation performance. So in these places, we can input both your data that you have collected for your cell, as well as these foundational models. And we can train the model to find what is the degradation profile or the temperature performance for your actual system and your data. And these same training methodologies can be applied for the defects, the distributions, really any kind of thing that you wish to look at. Yeah,
and if I may add to that, generally speaking, what we try and do is we try to take our partners or our collaborators or our customers testing data and then validate our models with that data. And what we're showing you here is sort of like a typical set, an example in some sense, but really like the thing that we are keen to do is to make sure that we take in your data and then just take in your data and then validate our models as well. So this is something that we do with a lot of our customers. So we are looking forward to sort of working closely with you and making sure that the batteries you're looking at represent your batteries. So there's a few other questions. So which physical phenomena is being considered in this in the degradation? What are the parameters being considered to assume such rate of degradation? Can you talk a little bit more about these assumptions? So I'll let you talk about the SEI capacity framework.
Yeah, so like Ranjan mentioned, we're working with an SEI capacity fade model. So physically how this works, there's a parasitic side reaction on the anode, and this consumes some of the overall intercalation. And eventually this builds some layer which grows on the anode and leads to a deduction in the state of health. So this is an empirical model, but we found it to be pretty good for some sources from the literature.
So there's another question on what are our email addresses to get in touch. I think the best way to follow up is to email sales@juliahub.com. I mean, it's we're just an email away after that, but it's sort of our process. So if you could
do you want to
email
click on the slide, maybe?
Yeah, let me just get there. So so here sales@juliahub.com. Very, very soon you will get connected with us, and we will talk to you, and we would love to discuss more with you about your application. So another question is, what part of this is open source? What's closed source, and what's the pricing structure? So I can take that one. So this JuliaSim Batteries is a closed source library. It's part of our JuliaSim modeling and simulation product, which is also closed source. JuliaSim Batteries is a standard library within that. So generally speaking, in terms of pricing, there are two sources of pricing, right? So one is since all of our apps are on our platform, JuliaHub, so we have a particular platform fee associated with JuliaHub, and that platform fee varies based on the tier that you want, right? That we have tiers for individuals, teams, as well as companies, enterprises. So based on that, the platform fee varies, and then of course, and then JuliaSim is an add-on to that platform fee. So it's sort of a subscription SaaS-based model, please, we're happy to give you specific numbers on all of these if you get in touch with us and we discuss privately. Yeah. So I hope that helps. Let's see if there are any more questions from the chat. I'll give it a minute. The other part I wanted to sort of mention to everyone is, to be fair, there's the question is, what is open source? While all of the stuff I told you is closed source, the part that's open source is sort of our general modeling and simulation package called modeling toolkit.jl. It's a general multi-physics sort of model specification package. All of our standard libraries for our batteries and HVAC libraries do not come with that. So that the only standard library you get with that are like very basic electrical, mechanical, thermal, and hydraulics components. So that is the way you could get started on general multi-physics software with JuliaSim for free by downloading modeling toolkit.jl. But to get started with JuliaSim batteries, which I'm sure is what you're referring to, none of that is open source. It's all closed source. Yeah. Otherwise, I think that's it for questions. I don't see any more. Thank you so much, everyone, for joining us. Please do get in touch with us on sales@juliahub.com. And again, if you're emailing us with technical questions, that'll come to us, and we're happy to answer them. But of course, yeah, and but this is the email to contact us on, and yeah. We look forward to interacting with all of you and validating our stack against your testing data, and coming up with some interesting analysis for you as well. So yeah, do get in touch, and thanks for joining us today. Please do remember that we have another webinar coming up on April 17th, where we talk about how you swap in and swap out chemistries and understand the results and so on. And please do join us for that one. Otherwise, thanks so much again for the time, and we'll see you at the next one.
Thanks,
Ciao.
everybody.